Hello, everyone. Welcome to ACME Journal of Computing Information Science in Engineering JCISE, a monthly Spotlight Talk webinar. Today it's my pleasure to introduce Professor Chabo Fahad from Stanford University as a speaker today. Professor Fahad is well-known and expert in the computational mechanics, multi-scale multi-physics simulation, looking into the recent uncertain quantification, recently also looking at physical information learning. And as a little background, and Professor Fahad is a Vivian Church-Hoff Professor, as well as James Anna Mario Spiker Chair of Department of Aeronautics, Department of Mechanical Engineering, and Institute for Computational Mathematical Engineering. Professor Fahad has been contributing tremendously in the field of computational science, and he has received several honors, including elected member of U.S. National Academy of Engineering and the UK's Royal Academy of Engineering, as well as Lebanese Academy of Sciences, and 3 other honorable doctoral degrees, and as many others honors. For today, today we will have the opportunity to learn the latest research, which is the paper published at JCISE. The title of the paper is Acceleration of a Physics-Based Machine Learning Approach for Modeling and Quantifying Model Form Uncertainties and Performing Model Updating. Chabab, please move forward.
Thank you, Jan. Thank you very much for this generous introduction. Let me start by acknowledging the contributions of my co-authors, Mary Jo Elsie, who's a graduate student and working leading this paper, Philip Avery, who is a staff research scientist, and my colleague at Notre Dame University in Lebanon, Shadi Ignatius. We are focusing on this paper on 3 interdependent and very much intertwined objectives. One is digital twinning, and we will start with a digital twin of the prototype type, and I'll explain what that is. And then we're interested in performing model form uncertainty, and I'll explain very well what that is. And in order to do this model form uncertainty, to be able to do it in a computationally tractable amount of time, we will have to build another digital twin of the instance type, so it's a different digital twin. And then once all this is in place, we will be doing a model updating, and the model update will allow us simultaneously to do the model form uncertainty. So in a nutshell, we start from a digital twin of the prototype type, and then we use it to perform model form uncertainty quantification. And then we realize that we need another digital twin of the instance type. And once the model form has been quantified, then we can do a model updating, and this will give us an even better DTI. Now, digital twins is a big topic. It means different things to different people, but there is a community that classifies it in 3 different types. A digital twin prototype, which essentially a digital twin that exists before you have built whatever physical asset you're trying to build a twin for. And it's used for doing the design, the analysis, or even the processes like certification of a design or of an analysis. It is essentially a rebranding of the old CAD and modeling and simulation. It's a little bit hotter word, but essentially it's the same old thing. Where things becomes more interesting is when you go to a digital twin of the instance type. So this is a digital twin that you build after the product has been manufactured and when it has been deployed. And that because when it has been manufactured and deployed, you can equip it with sensor sensor can send data to the digital twin counterpart, and then the digital twin could update itself by learning from the data, and this will give you a much better model. Now, you can have a version of the DTI that is known as the digital twin aggregate, and in that case, it's the same concept as a DTI, but instead of learning from one individual instance of the product, you can learn from a family of that product, like a fleet of cars of the same model or a fleet of airplanes of the same model. This whole thing is the result of the Industry 4.0 thinking, and it has applications in crisis management, predictive maintenance instead of scheduled maintenance, quality control, warranty optimizations. So that's why there's a lot of interest in this topic. Now, model form uncertainties are present in almost any situation where you use a model. I would say the minute that you decided to model something, you're introducing model form uncertainties. We have to distinguish them from parametric uncertainties in the sense that I am not referring here to the parameters of the model, but really to the fact that we have a lack of knowledge of the physics that are governing the problem. And therefore, when we postulate a certain model, the model itself is uncertain. So if I go, for example, to structures, the constitutive model that I choose to use in my computational model could bring in uncertainty. If there is a multi-scale aspects that I have homogenized, that brings in uncertainty. If there are free play modeling errors that I neglected or assumed certain types of boundary condition, they were not exactly the correct boundary conditions, joint links, etc. All these brings model uncertainty. They are of the model form type, so which are not of the parametric type. What is really interesting is that the model form uncertainties, or what I'll be referring to as MFU, are far less studied in the literature than the parametric uncertainty, probably because they are a little bit harder to deal with. Now, whatever uncertainty you choose to deal with, whether it's parametric or model form, model reduction or surrogate modeling in general is always advocated or mentioned at least because a classical way of quantifying uncertainty is to perform stochastic computations, Monte Carlo analysis. So this means that you're going to be very computationally intensive. You have to do many, many simulations. And that for surrogate modeling or model order reduction, depending on what you're focusing on, is always touted as a way to do these things. What is really very important here is to realize that every time you use a surrogate model, whether it's a reduced order model, whether it's a Gaussian process, or whether it's a neural network, you are bringing model form uncertainties because each one of these tools have their own uncertainties. And therefore, what is really important is that when you're trying to model and quantify uncertainty in an original high-dimensional physics-based model, any tool that you bring in to deal with this uncertainty, if it brings its own uncertainty, you have to account for it. And this is what we will be doing in this paper. Now, one thing I have learned from the review process is that one should explain clearly what are your key performance indicators? How do you judge that your objectives have been very well met? So as I mentioned here, I would like to, on behalf of my co-authors, I would like to achieve 3 objectives that are intertwined. Doing a modeling and quantification of model form uncertainty, doing digital twinning, and doing model updating. So how would we know that we're doing well on this? Well, if you focus on the picture on the right, which summarizes pretty much what I'm explaining on the left, you see that I could have a target response, and this is a target response that you see it here in dark blue. It looks almost like black on the picture, but it's a dark blue. And I would like to quantify the MFUs, and I would succeed if the confidence intervals that I will compute for the problem that I'm simulating here, they have to contain the target response. Typically, that target response is known at a few sensors. So my key performance indicators, I'll evaluate them at these sensors, but obviously we're interested elsewhere in the structure too. But this picture just focuses on defining a KPI here that says that the interval of confidence has to include everywhere as much as possible the target response. Then I have an original model that you see in red that attempts to predict the target response, and it does a decent job, but they're not an accurate job. You could see, for example, where my arrow is, you have a significant error of the red curve with respect to the dark blue curve. On the other hand, when we will do a model update, and I'll explain how we do the model update, you could see that I get a statistical model update. So I look at its mean value that is shown in green, and you can see that the green not only sits inside the yellow ribbon that quantifies the uncertainty, but it's also much closer to the target response than the original model, which was the red model. And therefore, I have been able to update my model so that it tracks much better the data. And obviously, we're interested in the updated model elsewhere where we don't have sensor data, but we're using this KPI to see if at least where we have sensor data, we have been able to learn from it, and we have been able to apply it to measure the performance of the technology. Now, here are my backdrop computational model. So I start, in this case, let's say we're interested in a computational and structural dynamics problem. So I start from some nonlinear finite element model that has hysteresis variable, has internal forces, external forces, and it's parameterized by mu because, for example, it's going to be used in parametric computations or is going to be used for design, etc. And then I build a projection-based reduced order model, which means that I look for the solution of this problem in a affine subspace that's going to give me some approximation. For those of you who are not familiar with this, you can think of, for example, modal superposition, except that this is not a modal superposition given that we are in nonlinear regime, but it's one approximation that will allow us to reduce the dimensionality of the model, and we build a reduced order model that is written below, and the subscript R is to say that this is a reduced matrix. So M subscript R is V transpose MV, which is the reduced mass, and F subscript R internal, this is the projection of the internal forces onto the subspace represented by V. So I get my reduced order model, and this is in order to be able to go much faster when I needed to do stochastic computations. Now, most of the time, model reduction itself is not enough. You need to do also something known as a hyperreduction. And that's because when you have projection quantities, like if I go back to my reduced order model here, every time, since this is nonlinear, every time that the solution change, I have to recompute V transpose times F internal. That projection can be very expensive, and therefore repeating the calculation of these projections can degrade the performance to the point that there is no point doing model reduction. So we came up with a concept of hyperreduction that simply says that if you go to a finite element like this engine that you can see here, a solid model of an engine, and when you need to compute some quantities, like for example, the projection of a vector onto a subspace represented by a matrix V, you can do all these are matrix and matrix vector multiplications. You can do them element by element. And then the idea here is that if you can do them element by element, perhaps we don't need to do them on the entire mesh. We can simply pick a few elements into the mesh, and then we can do a cubature, which is a generalization of a quadrature rule that says that if I train very well, so that's a machine learning process here. If I train very well that cubature rule, I can probably replace all this mesh that you see here only by the blue points. And I show you here where their locations are onto the mesh. And I can compute my assembly of the finite element process on a subset of these elements, and therefore I can do it in real time. More importantly, we developed about almost a decade ago an approach for doing this that has become very popular because it does this approximation while simultaneously preserving the Lagrangian structure of the second order dynamical system. And as a result, it maintains numerical stability and it maintains accuracy to a large degree. So if I just show you what we are capable of doing with such a hyper-reduced reduced order model, this is the simulation of the underbody blast of an Ares tank at ARL, at the Army. So we're looking at a model here that is J2 plasticity. It has nonlinear kinematics, large deformations. It has also contact. So it's a highly nonlinear structural model. And we're looking at the response of the vehicle for a blast that is caused by 20 kilograms of TNT. This is explicit transient dynamic analysis. The model has almost like 500,000 degrees. It has, 2 million degrees of freedom. And then I'm going to reduce its mesh size from a little bit over 300,000 elements to less than 600 elements. So you see the CAD on the left, you see the mesh in the middle, and then you can see those dots in blue and red. So this is the reduced mesh. I'm going to do all the analysis only on the reduced mesh, and I can reconstruct the solution everywhere. And this is the simulation of the blast that you see here. And then if I look at how well I can predict the high dimensional simulation using my reduced order model. So I'm going from 2 million degrees of freedom to a reduced order model that has only 31 degrees of freedom. And you can see that in this particular case, if I look at a sensor that is the von Mises stress, I reproduce very well the solution. And instead of taking 48 hours on 250 cores, I can solve the problem in 21 seconds on one core. So it's almost real time. And all this is to say that if I want to do now stochastic computations and Monte Carlo simulations very rapidly to do my mother form uncertainty quantification, I can use such a technology, HPROM, to construct a real-time digital twin of the prototype type. So it's a digital twin that will run in real time, but this is a digital twin that doesn't learn anything. So in order to make it learn something, this is where I'm going to get now into the modeling and quantifying of the mother form uncertainty. And you can see how the two things are really tied together. So if I go back to my original problem, this is most of the approaches for performing UQ typically would operate like this. They would go to the partial differential equation that represents the model. They would randomize the coefficients and assume a certain distribution of the probability. And then after they randomize it, it becomes an input-output problem. If you know what is the uncertainty in your input, what would be your uncertainty in that output? And this is the problem of the propagation of the uncertainty. Well, there is an issue with this approach, is that if you assume that you have an experimental data that is sitting at this point that you see here on the slide, and then if I take my deterministic model and I vary my parameters any way I want, and they will never include the experimental data. I could never reach the experimental data. So randomizing the coefficients of the partial differential equations are not really going to help very much, except of telling me a little bit about the statistics of the uncertainty. On the other hand, this is, and we cannot do model updating in that case. On the other hand, Christian Suarez and myself, about 4 or 5 years ago, came up with a different approach for dealing with model form uncertainties. And this approach says, instead of randomizing the coefficients of the partial differential equation, or if you want the coefficient of your physical model, we're going to randomize the subspace in which we are looking for the solution. So if this is a finite element model, it's almost like saying we're going to randomize the shape functions, except that this looks like it's a little bit way too expensive to do that. But fundamentally, that's what we're talking about, is to randomize how we compute the solution. And therefore, when we randomize how we compute the solution, we can expand the scope of the approximation without increasing its dimension. And we can hope to be able to enlarge the space in which the solution is being computed so that it can capture the experimental data. And when it captures the experimental data, we would have really extracted information from the experimental data and embedded inside the computational model. And this is where the learning process is and where the model updating is. And that will help us assess the model form uncertainty. So the way we do this is we take the reduced basis, since we're going to, as I mentioned earlier, we are going to account for the model form uncertainties that will be inherited from model reduction, in addition to the model form uncertainties that we have been trying to target, which come from the original model. So I'm going to randomize my reduced basis, since it represents a space where I'm looking for the solution, but I can't afford to randomize every one of its coefficients. So I'm going to randomize it with a finite number of hyperparameters that is much smaller than the number of coefficients of that reduced basis. And when I randomize the reduced basis, I need to guarantee that the columns of that basis remain linearly independent, so that after randomization, V remains a basis. And therefore, I'm going to do the randomization on what is known in mathematics on a compact Stiefel manifold, which means I want to randomize V so that after randomization, V satisfy V transpose Q V equal the identity. So that makes V an orthogonal matrix, which is more than when I was trying to achieve. If it's orthogonal, it's certainly linear, its columns are linearly independent. So this is why we choose to make it this way, because this will guarantee linear independence of the columns, and the fact that after randomization, the deterministic basis will remain a basis. Throughout the rest of the slides here, any regular font is a deterministic quantity, and any bold font is the randomized version of that quantity. So the bold indicates randomization. So this is how we do the randomization. We start from a random matrix where the randomization is performed using a certain number of hyperparameters. And that random matrix has the same size, same dimension of the reduced basis. It doesn't necessarily satisfy V transpose Q V equal identity, so it doesn't live on the Stiefel manifold. So now I'm going to do a series of transformation to bring it to that manifold. So first, I look at the deterministic basis. So that's the V without the bolded font. It lives on the manifold because the V is an orthogonal matrix. And then I take the tangent to the manifold, because that will give me a linear space. And I will map the U onto that tangent. And this will give me this matrix Z. And then I will need to do a polar decomposition to bring the Z onto the manifold. And this will give me the matrix V bold, which is the random reduced basis that I have been looking for. If I look at the physical interpretation of what I'm doing, you can see that the randomized reduced basis V is equal to the deterministic reduced basis V plus some perturbation that you see here, and the whole thing multiplied by an operator that comes from the polar decomposition. And this perturbation is with the Z matrix, which lives in the tangent plane, which means that I take the deterministic reduced basis, which means the subspace that contained my solution from the deterministic model, and then I try to explore some departure from there. What if I have modeled my solution differently, which means what if I have tried to model it to correspond to a different partial differential, for example, but I need to stay in the tangent plane so that I don't go too far, and then that would be like the model is completely wrong instead of simply the model having some uncertainties that need to be dealt with. Now, S is a hyperparameter here. How far do I need to go? So it's something that needs to be determined. And U has its own hyperparameters alpha. And then in the paper, we explain how we get a number of hyperparameters that is of the order of n squared, where n is the size of the reduced order model. So I can start from a model that has million degrees of freedoms. My reduced order models will have tens of degrees of freedom. And then my hyperparameters alpha will be of the order of 100 hyperparameters that needs to be determined. So how are we going to determine them? Before I tell you how we're going to determine them, now what am I going to do with this randomized reduced basis? So I'm going to go to my reduced order model, substitute the deterministic basis by the random basis. This will give me a random reduced order model that is boxed here. The hyperreduction carries out, so I have a randomized hyperreduced order model. And then every time I want to do a Monte Carlo analysis, this is where I'm going to do the Monte Carlo analysis with this randomized reduced order model, so that I can get, for each different value of alpha, I will get a different solution. So I'm going to be computing a family of solutions. And now the idea is to bias the alphas such that this family of solutions that I can compute can capture the experimental data when I have it. So, and in order to be able to achieve this objective, I'm going in the spirit of machine learning. I am going to build a loss function. And when I build that loss function, I'm going to say that if I have data, and let's assume that the data that I have is statistical, if it's deterministic, well, it's a simple particular case of the statistical case. I'm going to say that I would like that my stochastic reduced order model, when it generates a families of solution, I would like that the mean value of that model matches the mean value of the data, and that the standard deviation matches the standard deviation of the data. And therefore, I built a composite cost function that is weighted with respect to the mean and with respect to the standard deviation. And now I can form an inverse problem that says that I need to minimize that cost function, and that would give me the value of alpha, which are the hyperparameters of the randomization, that would allow me simultaneously to quantify the effect of the uncertainties after I have modeled them, and update the model, since once I have alpha, I have V of alpha, and then I have now a model that is updated. And this can be explained as I would have simply extracted information from the data that was not captured by the way I built my model. And because the alpha, which gets this information from the data, affects the V gets into the model. So I have extracted the information and I have found a way to infuse it inside the model. Now, this has been 4 or 5 years ago, and we have had some challenges. And the challenges have been the fact that this problem is highly nonlinear, highly non-convex. It has O of n squared, where n is the reduced dimension of the problem of hyperparameters. So it was still expensive to compute, and it was very hard to get a robust solution given that if you get a local optimum, there is not a very good optimum, which is a problem for all machine learning problems, then it will be difficult to improve really the model and model and quantify the uncertainties very correctly. So we need some kind of global optimum and not a local optimum. So we have done recently 2 enhancements for this. The first enhancement is to say we are not going to rely on a finite difference computation of the gradients of this cost function by whichever package we are using to do the minimization. We are going to compute this analytically ourselves outside the package. That's the first one. And the second one is that we want to push the theory further to reduce the number of hyperparameters from O of n squared to O of n so that we can solve the problem much faster. So both of these 2 enhancements would provide simultaneously better robustness, particularly the first one, and better speed, both the first one and the second one, because if we have much better gradients, the optimization process will converge faster. And if we have fewer variables, it will converge even better. So that has been a little bit the objective. Now, if you look at this cost function, it is really scary when you think that you want to compute the analytical gradient, but we have done that. I guess graduate students are fantastic at doing this kind of job. So there is a complex web of operation here that underlie the construction of the cost function. There are reduced order models that you need to differentiate. There are stochastic calculations that you need to differentiate to be able to compute all these gradients. And this is essentially how it goes. So if my observable, let's say, that is coming from the reduced order model, and we take the simple case where the observable is at every degree of freedom, just to simplify the notation, then if I look at the gradient of the mean with respect to alpha, at the end of the day, when you carry out the analytical sensitivities, it turns out that you have to compute the derivative of the generalized coordinate vector with respect to the reduced basis, and you have to compute the derivative of the reduced basis with respect to the hyperparameter alpha. And this can be done. The first one is relatively straightforward. To compute dv by d alpha, it's a lot of patience, and there is a complex web of analytical differentiations that you need to perform. But now to compute dy by dv, that's a tensor, that's a little bit harder. So we have built a discrete adjoint methods to build this. And for example, if you have an implicit Newmark beta time integrator, you can see here in the box a classical discrete adjoints that follows the discretized and differentiate paradigm, and that will give you the dy by dv. So all this is analytical, and then this will give you a much better gradient. Now, the much more interesting thing here has been how do we reduce the size of the hyperparameters? So the hyperparameters, where the vast majority of them constitute the upper diagonal of this matrix of covariance sigma. And the idea is that any one of them, this is a Cholesky decomposition, can be a hyperparameter. All what we know from the theory is that at maximum we have n squared, but it could be less than that. So first we have run a old optimization method that is known as taboo search. That is very interesting because you give it as a list of candidates optimization variables, which means not only you're interested in optimizing a function, but you're also interested to know what are really the good optimization variables, and it will give you that information. And when we did that, and the way it works is that every time it explores one possible candidate, like you see here in green, and it sees whether really it's going to improve. If you use it as an optimization variable, you're going to improve your objective function or not. So bottom line, using simple problems, that taboo search showed us that actually we don't need all the O of n squared. So you can see here taboo search for a simple structural analysis problem like the one you see here. has identified sparsity in the matrix of the covariance, and then it's telling us that we need much fewer than that. So when we ran with the full hyperparameters, this is what you see on the right, and then we rerun them with a fewer hyperparameters as taboo search tells us, you can see that we get the same result pretty much, even slightly better, I would say, with the reduced number of hyperparameters. All the confidence intervals look good. And so this was a clear indication that we can do much better than O of n squared. So how do we do that, though? Well, this is where machine learnings come back and the theory of features. So when we generate the random matrix U, instead of building it in a certain form, the way we have been randomizing it so far, which is heavily grounded in partial differential equations, well, we decided to take a computer science approach and take snapshots, like in a Monte Carlo simulation, all those realizations that we're going to do anyway afterwards. We take snapshots of this random matrix U, we pass them to an autoencoder, and that autoencoder will give us the number of features that it identifies in this randomization, which means it's almost like trying to say, you don't really have big N times little n, and not even O of n squared independent variables here. You can rebuild all the information from a much smaller number of features. And typically, the autoencoder has been returning to us something very consistent with taboo search. Taboo was saying 3n. Here we can find 2n. Taboo search was very expensive. If we used it only to get the idea, the autoencoder, you build it once for all before you start your optimization. And then it tells you that you're going to find like 2n features, and this is what we have been doing. So instead of randomizing U as some function G times one hyperparameter beta multiplied by a upper triangular matrix that had n squared over 2 hyperparameters, now we replace all this by the features that the autoencoders tell us, and there are 2n of them. So let me show you quickly now some applications and conclude the paper. So first, a moderate difficulty application. This is the transient structural response of a supersonic nozzle to a thermal load. So this is a parametric model that has 2 parameters, the length of the nozzle and the width of the nozzle, that can go anywhere from an elliptical section to a circular section. And so we built the finite element model, has about 100,000 degrees of freedom. We built a reduced order model for it that has only 14 generalized degrees of freedom. So we can run any stochastic analysis 10,000 times faster than originally. And therefore, we can do the minimization for the hyperparameters problem very fast in that case. So when we do the UQ on this and we do the model updating, let me show you first the model updating. So you have the target solution in solid black. You have the deterministic solution in dashed line. Not too bad, but not perfect. So the idea is that the stochastic digital twin type of model, DTI, that's going to learn from the experimental data. So there were a few sensors here that were picked to be able to get experimental data. It's a simulated experimental data. You see that the update didn't work very well, and that's because we were using finite difference gradients. So you see the signal in light blue that is worse than the deterministic signal. On the other hand, keeping everything the same and simply replacing the 107 hyperparameters by the 44 features identified by machine learning, well, you get, in this case, a much better local optimum, probably very close to a global optimum. And then you can see that the stochastic HPROM, its mean value, which is in light blue, starts now matching much better the target response than the deterministic model, showing the success of the model updating. The same thing now, if I do the analytical gradients, and I even keep the old way of doing the hyperparameterization. The analytical gradients you can see here do a very good job. So when you combine the analytical gradients and the autoencoder to reduce the number of hyperparameters for 100 to 40, you see that you're going to get even much better. So now if I look at the key performance indicator looking at the confidence intervals, you can see that with finite difference gradients and with the 107 hyperparameters, the confidence intervals don't look great at all. Now the same technology, but using analytical gradients instead of leaving it to the optimizer to compute by finite differences, the gradients start doing much better. You can see now that the confidence interval bracket the signal everywhere. And then if we combine the analytical gradients with the autoencoder, we get even much sharper treatment of the uncertainty. Let me now conclude with this more challenging problem. This is the problem of the crash analysis of the front bumper of a Honda Accord EXL. We have been successful at building a reduced order model, not for a quantity of interest, for the entire dynamics of the crash of the front bumper. So we built a finite element model that had something like 226,000 degrees of freedom. We reduced them to 20 only, and we trained it so that it's operational even at the unseen point. And this is the crash that you can see here against a wall. And then when we look at the model form uncertainties here, you can see now the sensors that is obtained in black. You can see the deterministic model that's doing not too bad, actually, for where the data was given to us. So you can see this, this is here in dashed line, and this is with the ROM so that you can go fast. And you can see the updated ROM in light blue, and then it tracks much better the experimental data. And we can see here the intervals of confidence that at the beginning are very narrow, and then when they certainly increase here to indicate there is more uncertainty there. So this is at two different locations, so two different sensors on the left and on the right. And this was done with the features. We reduced them from 212, the original number of hyperparameters, to 61. And you can see that in this case, the optimizer functions much better, and the updated model in light blue here starts matching much better the target than it was doing it on the left. So in conclusion, NPM stands for nonparametric probabilistic method. It's a framework for extracting information from data. This data can be experimental or high fidelity numerical data if you want to use it to inform a reduced order model. And it extracts information from data that is not captured by a high dimensional model or its ROM counterpart, and it infuses it into it to do a model update and to help quantify first model and then quantify the model form uncertainty. So in that sense, you get a digital twin of the instance type. So it's a digital twin that will learn from experimental data or test data in general, and then will update the model accordingly. It is characterized by a non-convex optimization problem. That's its bottleneck. Like many inverse problems, they are very hard to solve. Regularization is not always trivial for these problems. So the presence of an inverse problem causes difficulties both in terms of robustness and performance. And the two things that we have added here recently is an autoencoder approach to reduce the dimensionality of the hyperparameter space. And this improves dramatically performance, and the analytical computation of the gradients. And this has improved very well the robustness of the approach. Thank you.